Taste, smell, they are some of the most important sensations. From birth, we have been engulfed in an array of flavors and smells, from when we first tried disgusting pureed peas as babies and scoffed at the pungent smell, to refreshing soft serve on a hot summer day and the smell of coconut sunscreen and fresh-cut grass. With sensations of taste and smell being such integral parts of our lives, it leads us to wonder how exactly do they work? The simple answer is that what we perceive as taste and smell is a result of complex interpretations and processing of chemicals that stimulate the perception of different flavors and odors. In terms of taste, the sensation of taste is activated when certain classes of chemicals come in contact with specialized epithelial tissue receptor cells in the tongue, palate, throat, the epiglottis, and the upper esophagus. The array of taste stimuli detected at the periphery are processed alone and/or in combination to stimulate the perception of nutrients or toxins. These perceptions drive complex ingestion or rejection behaviors and initiate physiological processes that aid in the digestion and assimilation of food. Human taste perception can be categorized into one or more combinations of the 5 taste qualities, being sweet, umami, salty, sour, and bitter. Regarding how chemicals are perceived as taste, sweet sensations are associated with the presence of simple carbohydrates. Umami, or savory taste, is generated by amino acids and small peptides. Salty is associated with the presence of sodium and sometimes other ions. Sour taste is generated by acids, and bitter taste sensations arise from stimuli that are potential toxins, such as various plant alkaloids. Smell, also known as olfactory perception, works similarly to taste in that chemicals come into contact with specialized receptors that process the olfactory signals and relay them to the brain. Specifically for smell, odorants bind to receptors in the cilia or dendrites of the olfactory receptor neurons, each of which expresses one or more receptor types. Olfactory receptor neurons that express the same odor receptor send axons to the same glomeruli, spheroidal structures that consist of olfactory receptor neuron axon terminals and the dendrites of second-order neurons. In humans, these glomeruli form the olfactory bulb, in which olfactory signals are processed and relayed to the brain. In mammals, the olfactory system, being the system that perceives smell, is comprised of 4 different organs, these being the main olfactory epithelium, the vomeronasal organ, the Grunenberg ganglion, and the septal organ of Macera. The main olfactory epithelium perceives general odors from the food and environment, peptides and volatile amines that correlate to urine and other bodily secretions, and bicarbonate from the atmosphere. The vomeronasal organ detects volatile pheromones, proteins, peptides, and sulfated steroids associated with urine, stress, and illness. The Grunenberg ganglion also detects pheromones associated with stress. And finally, the septal organ of Macera, much like the main olfactory epithelium, detects general odors that are associated with food and the environment. In looking at the current applications of taste and smell, the coronavirus pandemic yields a novel opportunity to see how viruses can impact how we perceive chemicals that we encounter in our environment. For many people who have become infected with the virus, they report that they have temporarily lost their ability to taste or smell, and in some cases both. However, when I say loss of taste, I am not referring to someone's fashion sense, but rather their ability to taste food. Yet it would be a lot easier to tell if somebody had COVID if they suddenly started dressing in head-to-toe cheetah print. But getting back on topic, in terms of smell, the coronavirus is understood to infect cells that support neurons in the nose. While it was once believed that the virus infects the olfactory bulb in the brain, this is not the case. Recent studies have shown that the virus rarely reaches the brain. A team led by Sandeep Robert Datta, a neurobiologist at Harvard Medical School, has instead found that the cells that support the sensory neurons in the nose, known as sustentacular cells, are the cells that the virus is most likely infecting. Datta and his colleagues chose to focus on sustentacular cells as COVID attacks by targeting a receptor called ACE2 on the surface of cells, of which sustentacular cells have many. This suggests that the coronavirus infects the support cells, which leaves the odor-sensing neurons vulnerable and deprived of necessary nutrients. However, in looking at how the virus affects taste, little is known. However, in looking at how taste and smell interact, it sheds a little light onto how the virus may be contributing to a loss of taste. The senses of smell and taste combine at the back of the throat, and when you taste something before you smell it, the smell lingers internally up the nose, causing you to smell it. Those receptors in the nose coordinate with the activation of the taste receptors and enhance what we experience as taste. However, with the loss of smell due to the coronavirus, this does not occur. Although we commonly distinguish taste as one sensation and smell as another, both sensations work together to create the perception of flavor, which allows us to distinguish between sweet and bitter. Much like when someone has a reduced perception of flavor when they are congested, it is possible that the same concept can be applied to the coronavirus's impact on the perception of taste. For smell, Chapter 24 covered much of the organic compounds that olfactory receptors come into contact with. For aldehydes and ketones, they are perceived as pleasant aromas, such as those associated with pheromones, wood smoke, and spearmint. Esters are then responsible for many sweet odors, such as that of pineapple or other fruits. Amines are then responsible for pungent, foul-smelling odors associated with the decomposition of proteins. With taste and smell being such integral components of our everyday lives in that they allow us to have a sense of our surroundings, pun intended, they play a significant role in our safety and well-being. In being able to perceive chemicals such as carbon dioxide, hydrogen sulfide, ammonia, and methane, we can avoid consuming meats and dairy products that have spoiled solely based off of their smell. And in the unfortunate case that someone takes a bite of spoiled food, they can quickly spit it out due to the brain recognizing the chemicals present in the food that has gone bad. Additionally, smell plays a crucial role in preventing bodily harm in the cases of fires or gas leaks. In the instance of a fire, the sensory receptors in the nose can pick up upon the smell of hydrochloric acid, ammonia, carbon dioxide, hydrogen sulfide, and hydrogen cyanide, of which are the chemicals present during a structure fire. Similarly, in the cases of gas leaks, the sensory receptors can detect the markeptin, also known as methane thiol, which is added to natural gas to serve as an odorant to make the gas leaks easier to detect. In both cases, in being able to use olfactory perception to detect chemicals associated with common disasters, smell allows one to act in seeking safety before it is too late. Resultingly, smell plays a crucial role in saving people's lives daily. So next time you realize you have left the oven on, go to check to see if your milk is still good, or you bite into an overripe apple, you can thank taste and olfactory perception for keeping you safe.